further ado, I'm going to hand over to you.
Not a problem. Thank you very much. First thing is, well, thanks for inviting me along. I suppose we better see if I can get my screen onto yours. Right.
Give it a go.
Let's see if that works, shall we? Okay, are we up?
Yep. Excellent. That looks good. That looks good to me, Jay. Jay, just before we start, I'm just going to mute everybody off except you. Okay.
Okay.
So if we have any dog
no
barking,
problem.
you won't see other people's faces come up. So I'm just going to mute everybody, but please do carry on.
Well, nothing wrong with a bit of grunting and groaning in the background if absolutely necessary. But anyway, as I say, thanks very much for inviting me along. I do run the SpaceGuard Centre just outside Knighton. We're actually the National Near Earth Objects Information Centre as well now. And we deal with a subject that, frankly, it is relatively new. And in fact, it really shouldn't be new. It's new because we made a mistake. And in science, of course, that's pretty common. It's actually how a lot of science works. But this one actually dates back to Isaac Newton. He told us that the solar system was actually a fairly quiet place. Nothing ever changed. It was mechanical, predictable, and so on. But then along came people like Hutton, Darwin, Lyell, who told us that actually things do change, but they only change very gradually over hundreds of thousands or millions of years. And all of that really finished off the old idea of sudden catastrophic change. In the good old days, they knew jolly well that if you upset a god or something like that, something big and bad would come along and change everything. But that idea was really left to the stupid and the superstitious until we went into space. Because when we had a close look at the other planets, we began to realize that the old guys might not be quite as wrong as we thought. To show you what I mean, this is what the surface of Mercury looks like. It's covered in holes. If you go out to Venus, that one's covered in holes. And if you go the other way out to Mars, same detail. But of course, once you get beyond Mars, the planets aren't solid, big gas giants. And you wouldn't expect that sort of thing to be visible on a gas surface. But that's what Jupiter looked like back in July 1994, just after it was hit by a whole series of comet fragments. You can see the impact sites, those dark smudges towards the bottom. Now, when that happened, everybody thought it was a once-in-a-lifetime chance to see something actually hitting a planet. And it was, until the summer of 2009, when it happened again. And since then, we've seen lots of impacts on Jupiter. For example, this one was back in 2019. If you look at about 8 o'clock, you can see a nice big flash. Something's hit it, caused that flash. That flash is about the same size as the United States. But if you look at the moons of the gas giants, and the moons are solid, of course, we're back to square one. That's one of Jupiter's, I was going to say 79 moons, but this evening, the discovery of the 80th moon has been announced. So that's one of Jupiter's 80 moons, Callisto, covered in craters. Now, if you go out to Saturn, you'll find a nice little moon called Mimas. The big crater there was almost big enough to smash the moon to bits. Didn't quite make it. If you go out to Uranus and look at Miranda, that one was smashed to bits. Later on, because of the gravity between the fragments, they all clump back together again. But even out as far as Neptune, you'll still find moons covered in holes. So wherever you look in the solar system, everything's been battered to death. And before anybody says anything about Pluto, that one's covered in holes as well. But there's one big exception to all of this, and of course that's here. And people thought that for some reason the Earth had just got away with it. Until we started looking at the Earth from the outside. And that's when we realized we got that wrong as well. Nowadays, wherever you look on the Earth, we're finding craters. In fact, we've got just over 300 in the catalogue at the moment. But this shouldn't come as a great big surprise to anybody, because all you've got to do is look at the next door neighbour. Now, we share the same bit of space with the moon, so the hit rate there must be a pretty good indication of the hit rate here. We've got a team in the United States who watched the moon just to see if they can see anything hitting it. And since they started about 10 years ago, they've seen quite a lot. So things do hit planets. There's no doubt about that. Question is, what is doing the damage? And what can we do about it? Well, to find out what's doing the damage, we really have to step back a little bit to find out where all this stuff came from in the first place. How do you make planets? And that's relatively simple. When the sun first formed, it was surrounded by a disk of dust, gas. Over time, all of that material began to accrete, clump together into ever-increasing sized objects. And at the end of the process, we ended up with a few fairly large objects orbiting round the new sun. We ended up with the planets as we know them. We've got 4 small solid planets fairly close to the sun, then 2 really big gas giants, followed by 2 icy giants. But within our solar system, we've ended up with quite a lot of gas debris. The first area where we find this stuff is between Mars and Jupiter. That gap between the terrestrial solid planets and the gas giants. In there should be another planet, but it's not there. Instead, we've got all the little bits that should have clumped together to make one. That didn't happen because of the enormous gravitational perturbation by Jupiter. It simply stopped that planet forming. So in there, we've got a whole bunch of big lumps of metal and rock. And there's quite a lot of them. This is the current plot. All the green stuff, all the green dots are these objects, asteroids in the main belt between Mars and Jupiter. The ones in red all have orbits that cross or very nearly cross the Earth's. So each one of those is a potential collider, either now or in the near future. So the asteroids are simply bits of a planet that didn't happen. The other area that we deal with is way out beyond the orbit of Neptune. Out there, the disk of material around the young sun was too thin to make planets, not dense enough. So out there, we've got millions and millions of big lumps of ice and dirt. the big dirty snowball model for a comet. And beyond that, that belt of comets, the Kuiper belt, begins to sort of splay out to form a great big cloud of comets that surrounds the whole solar system, the Oort cloud. Comets, well, most people seem to think like they look like that, big fluffy things with long tails and so on. But actually, of course, a comet looks a lot more like that. A big, dirty snowball. The skin on the outside is a sort of tarry material. Inside, we've got ice, mainly water, but traces of other hydrocarbons, methane, ethane, ammonia, and so on. But if one of those moves towards the sun, it warms up. And as it warms up, the pressure on the inside of the skin builds up until eventually it'll crack. And when it cracks, you get jets of material coming out of the comet, dust, gas, and so on. These photographs are taken by the Rosetta probe, and you can see the jets coming out of the comet nucleus. But all this stuff forms a massive cloud right round the whole thing. And when all of that gets even closer to the sun, the solar wind begins to blow that cloud away, forming the tail. So the comet's tail is being blown away by the sun. But it does tell us that comets are unbelievably grubby things. They're really the solar system's equivalent of the teenager. Wherever they go, they're leaving a trail of dirt and debris. And every now and again, the Earth passes through one of those trails. And that's where we get a meteor shower. But the Earth actually picks up little bits of debris from comets and asteroids all the time, mainly because asteroids and comets are fairly small, so their orbits round the sun can be perturbed quite easily. And some of them develop orbits that cross the Earth's, and that's when we get hit by stuff. Not a big deal. As I said, it's happening all the time. The Earth picks up about 100 tons of stuff every day from space. It's mainly dust. But every now and again, we get something a little bit bigger. If that thing is about the size of a grain of sand or a grain of rice, for example, then we'll see it as a meteor, a shooting star. They burn up in the upper atmosphere, normally somewhere between 15 and 20 kilometers above the ground. So shooting stars are totally harmless. But if we up the game a little bit to something about, well, a few tens of meters across, say a small house up to a reasonable sized mansion, that won't hit the ground either. But what it will do is it'll pop in the atmosphere before it hits the ground, a so-called airburst. Now, back on the 30th of June, 1908, a little lump of comet, about half the size of a football pitch, came whistling in over eastern Russia, just over the Tungus region in Siberia. When it was still 5 miles above the ground, it popped. The explosion was about 1,000 times more powerful than the atomic bomb dropped on Hiroshima. The heat and the blast completely shredded the forest underneath. 800 square miles completely destroyed. It's about the same size as London inside the M25. But this sort of thing has happened, will happen, absolutely no doubt. You're probably familiar with the famous Chelyabinsk event back in 2013. It was actually on the 15th of February. Everybody on that day was expecting the close approach of a very large asteroid called 2012 DA14, due to happen at about 7 o'clock in the evening. But shortly after sunrise, a little 17-meter object barreled in over central Russia, and at an altitude of about 30 kilometers, it popped close, not over, but close to the city of Chelyabinsk. The yield here was about the same as 200 Hiroshima bombs. Luckily, there was very little structural damage in the city. The main problem here was glass. It was 120 seconds from flash to bang. That's more than enough time for people to realize something was up, go to the window to have a look, and off we go. So most of the 1,600 casualties here were caused by flying glass. But this sort of thing is not at all uncommon. It's uncommon to happen near a large city, but the Americans, for example, have just declassified their take on these airburst events, and they've been picking them up for decades. But those are fairly small. Now, if we up the game a little bit to something about 150 meters across, think football stadium size, then things change a bit, because this will hit the ground. And it'll hit the ground at about the same speed as it was traveling through space. So for asteroids, you're looking at somewhere between 35 and 50,000 miles an hour. Comets can be 3 or 4 times as fast as that. Now, when a thing like that hits the ground, it's not going to stop. It's like firing a bullet into the ground. It'll keep on going until the ground physically stops it. When it does, the comet or asteroid blows itself to gas. And it's that explosion that forms the crater. It also explains why all, or nearly all, meteor craters are perfect circles. But luckily, this sort of thing's fairly rare. What we need to know, though, is what sort of effect do these things have? Well, if we take a fairly small object, about 50 meters across, that won't hit the ground, it's an airburst, but the effects will take out a reasonably large city. If we go up to the 150 meter size, which we've just been looking at, well, that'll take out a small country. Belgium, Holland, something along those lines. A bit bigger than that, a 1 kilometer sized object, 2/3 of a mile across, well, then we're into a global catastrophe. If you want mass extinctions, well, then we need something bigger than about 5 kilometers across. But luckily, of course, these things are fairly rare. It's not the sort of thing you see on the news every night. But we do need to know exactly how often this sort of thing is likely to happen. And the best way to find out is by counting craters. We know how to find them. We know how to date them. We don't want to do it on the Earth. 2/3 of the Earth's covered by the sea. We've got weathering, we've got erosion, we've got plate tectonics. Where you want to count the craters is somewhere that's completely dead and completely stable. So we count them on the moon, our next door neighbor after all. And based on the crater counts on the moon, we can come up with a fairly robust frequency table that tells us how often we get hit by different sizes of object. Just before anybody begins to cringe, this is the only graph I've got. But if you look at the really big objects, the mass extinction events, we're looking in terms of millions or tens of millions of years between events. Not something to get overly excited about. But if you go down to our 1 kilometer sized object that does global damage, then you're looking in terms of a few tens, perhaps hundreds of thousands of years. But given the lifetime of a normal civilization, that's pretty significant. Go down to our Tunguska-sized events that just take out a large city, well, then we're looking in terms of years or decades. So we have a problem here, which is a little bit different to your normal natural hazard. Firstly, it's comparatively rare. That's a good thing in some ways. It's a good thing is it doesn't happen very often. It's a bad thing because it's rare and people haven't seen it on the TV, on the news. Therefore, it never happens. When it does happen, though, stand by. There is no upper limit to the amount of damage that an impact event can create. Every other natural hazard we know of, there's a theoretical upper limit to the amount of energy it can dump into the environment. With the impact hazard, there is no limit. But this one is avoidable. Now, you can't predict or do anything about earthquakes, volcanoes, tsunamis, that sort of thing. But this one is predictable and you can make it go away. On the predictable side, well, the first step, obviously, is to find any potentially dangerous objects as long as possible before they actually become a problem. So we obviously need a search program to look for them. Back in the late 1990s, when the light went on and people realized there was a problem, NASA was told to find 90% of all the potentially dangerous objects bigger than a kilometer across. To do that, they put together a sort of consortium of telescopes. For example, we've got the Linear program in Socorro, New Mexico. Spacewatch on the top of Tate in southern Arizona. The Catalina Sky Survey just outside Tucson. We've also got Pan-STARRS. This is a joint NASA United States Air Force project with a telescope, well, now 2 telescopes on the top of Haleakala in Hawaii. And using instruments like this, NASA has achieved that goal of finding over 90% of all the potentially dangerous asteroids bigger than a kilometer in size. In fact, we now think we're somewhere between 96 and 97%. But once they'd done that, and the score was we'd found about 24,500 near-Earth objects, Congress told NASA to go and look for much smaller objects, down to 140 meters in size. And that requires a whole new system, a whole new generation of telescopes. For example, the United States Air Force has moved its space surveillance telescope from New Mexico to the west coast of Australia to give us coverage in the southern hemisphere. The European Space Agency is developing its Fly-Eye telescope systems. Eventually, there'll be 4 of these, 2 in the Northern Hemisphere, 2 in the South. Right now, the first of the 4 is already up and running in Sicily. The real game changer in all of this, though, is going to be this one, the Large Synoptic Survey Telescope. Now, it's not finished yet. It should be ready about this time next year. It's going to be a big beast. In fact, the main mirror on this telescope is 8.4 meters across. That's the mirror before they started to polish it. It's not designed to find asteroids. It's actually designed to scan the entire visible sky from its site in Chile every 3 days. But while it does that, it's going to find bucket loads of asteroids. We also have a space telescope, quite useful because it's in the infrared. And of course, the atmosphere absorbs infrared, but the asteroids shine in infrared because they've been warmed up by the sun. Our current space telescope is the NEO-WISE, Wide Field Infrared Survey Explorer. It's a second-hand one. It was originally launched to map the entire sky in the infrared. Once it had done that, though, it was handed over to the Near Earth Object Project. In fact, NASA's just announced that they're going to extend this program for another 2 years. So we've got this baby for at least 2 more years. By which time, we rather hope that this one will be ready for launch. This is the Near Earth Object Surveyor. It's another infrared telescope, but specifically designed to look for asteroids. So we've got the technology to find these things. We do need to know what they're made of and how they're put together. And over the last couple of decades, we've had a fleet of spacecraft going to visit comets and asteroids to help us find out. We're even bringing stuff back. Hayabusa, Hayabusa 2, the Japanese spacecraft has actually landed, picked up samples, and it's actually brought them back. So we have those samples. The United States are doing the same thing with their OSIRIS-REx spacecraft. That's actually on the way home now. So we can find them, and we know roughly what they're made of and how they're put together. When we find one, though, we need to know where it's going, and that involves tracking it for a period of time. The actual calculations are a mathematical problem, but to do the maths, you need measurements. Measuring exactly where that object was at an exact time as it moves. These days, nearly all of that measuring's done by amateur astronomers, which is absolutely fine. They do a cracking good job. So we can find them. We know what they're like, or we're finding out what they're like, and we can track them. But when we find one that's coming, we have some choices to make. We have a number of options. The first option is to do nothing at all, just sit back and hope it all goes away, which it won't. So probably a pretty dumb thing to do. Probably explains why it's current British government policy. The second option is to go for the sort of Bruce Willis approach. Let's blow the thing to pieces. That's fine. It just depends how stupid you want to look afterwards, because all you've done is converted a predictable bullet into an unpredictable shotgun blast. The third solution is simply to turn a direct hit into a near miss. Give the thing a little nudge, just enough to guarantee that it misses. At the moment, we've got the NEO SHIELD project up and running. This is a European project to look at different deflection methods. All the targets are different. No two asteroids are the same. So you need a sort of portfolio of methods to deal with different types of target. For example, they're looking at kinetic energy. You literally smack something into the side of an asteroid to push it off course. That's actually going to happen mid next year, when the American DART spacecraft actually hits a very small asteroid to see how much its course is deflected by. You may want to use a process called ablation. Now, the idea here is that you heat up one particular spot, it'll vaporize, the vapor jets outwards, and that produces thrust in the opposite direction. A slightly cruder way of doing that is the nuclear option. You pop your device some distance away, and it's the heat and the radiation that ablate the surface. But perhaps the most elegant way is to use gravity. You park a spacecraft next to the asteroid and then edge that spacecraft away. The mutual gravity between the two all tug the asteroid in the same direction. If you've got enough time, that's almost certainly going to be the method of choice. But over the last few years, people have realized that none of this can be done by a single nation. The European Space Agency is now part of the game, including that DART mission. The Space Situational Awareness project now includes the near-Earth object hazard. But perhaps more important than that is we now have the ear of the Security Council at the United Nations. They're putting together this international framework to deal with the issue. So things are moving, but there are a couple of elephants in the room. Firstly, I showed you this graph a little bit earlier on. We can estimate the impact rate over long periods of time by counting craters, especially on the moon. But the big question here is that impact rate steady over time, or do these things come in clusters, in bunches? Now, until recently, we've sort of assumed that the rate is constant. But studies of craters on the Earth show that that is not the case. It's not a constant rate, but we have been hit by bunches of these things clustered in time. We've also assumed that the current near-Earth asteroid population is steady, just maintained by leakage from the main asteroid belt between Mars and Jupiter. But it takes tens of millions of years for an asteroid to drift from that belt into a dangerous orbit. So that population of near-Earth objects shouldn't change a great deal over that sort of time. But it does. The thing is that leakage can't possibly supply enough asteroids to maintain the population of large near-Earth objects that we can physically see, or account for the number of large impact craters, which we see both on the Earth and the other inner planets by a factor of 10 or more. We also have no geological record of the airburst events like Tunguska. They leave no craters. Now, one explanation for all of this can be found in things called centaurs. These are comets that come in from beyond Neptune that reach the inner solar system, having been bounced around by the gravity of the gas giants. Initially, they behave like both asteroids and comets. They look like asteroids, but occasionally they show cometary activity like outgassing. It's been estimated that there are a lot of these things in the solar system and that they're quite big. Their orbits are perturbed. On the Kuiper belt of comets, they become Neptune crossing. When they do, they're then classed as centaurs. But their orbits are chaotic. They change very quickly as they make repeated close approaches to one or more of the big outer planets. Some will move into Jupiter crossing orbits, and from there they can be deflected quite easily into the inner solar system. This is actually happening at the moment to what was originally called an asteroid, 2019 LD2. Now it's classified as a comet. Now these centaurs will either collide with the sun or a planet, or be thrown out into interstellar space after a gravity slingshot by one of the giant planets. But comets are fragile things. They have a nasty habit of breaking up when heated or put under stress, gravitational or otherwise. We know that comets can disintegrate. We've seen it happen. But the disintegration of a large comet in the inner solar system will produce a mass of dust and bigger bits that could bombard the inner planets for as long as 100,000 years. Now, if we accept that large comets arrive every now and again, disintegrate, and produce increased terrestrial bombardment episodes, then our impact cratering should be episodic. And that's exactly what we see in the impact record on the moon and on the Earth. We could also look at the amount of dust in the solar system. And right now, there's an awful lot more than we would expect. In fact, the amount of dust we see suggests that a large comet, possibly as big as 100 kilometers across, disintegrated in the inner solar system within the last few tens of thousands of years. The effects of running through the debris trail of a large comet could involve the dumping of millions of tons of fine dust into the upper atmosphere. Added to that, you could expect the arrival of hundreds, even thousands of atomic bomb-sized bolides over a space of a few hours. As for the dust, detailed modelling of dust in the atmosphere was done in the context of a nuclear exchange. Dusting would reduce the level of sunlight, possibly down to that of moonlight. And as a result, global cooling would be sufficient to destroy most agriculture. In fact, two such historic episodes have been linked to such events. A sudden global cooling about 12,800 years ago led to the simultaneous collapse of primitive societies in Southwest Asia and North America, and a massive decline in large animals or mammals in North America, Europe, Asia, and Australasia. This event is known as the Younger Dryas boundary, and this is accompanied by a huge amount of geological evidence of some huge global disturbance. Apart from the effects of dust in the atmosphere, a swarm of fireballs at the same time could well have started wildfires over a significant part of the Earth's surface. And surprisingly, or not surprisingly, there's a huge amount of charcoal and soot at the Younger Dryas boundary, evidence of huge, extensive burning. Then around 2350 BC, a number of very early civilizations throughout the Middle East, India and China, all collapsed simultaneously. No link between them, but they all collapsed at the same time. We found evidence for a number of asteroid and comet impacts at exactly that time, as far away as Peru, Spain, and Syria. Now, we don't know how long the cooling event lasted, but it could have been anything between a few decades and a couple of centuries. The breakup of a large comet in the inner solar system may, every now and again, generate a huge population of small impactors, Tunguska-sized objects. Further evidence for this comes from meteor and fireball studies, which indicate that the number of impactors, the small impactors, less than a few tens of meters, could be up to 10 times higher than the estimates based on our telescopic surveys and crater counts on the moon. So it looks like there's something badly wrong with our estimate on the number of small impactors, perhaps 10 to 50 meters in diameter. But the arrival of a centaur in the inner solar system brings a massive risk of dust and smoke in the atmosphere, hundreds of times worse than that expected after an all-out nuclear exchange. It also seems that such events happen at least 100 times more often than the big globally threatening asteroid impacts. Now, whether the disasters in 2350 BC and 12,800 years before present were in fact due to cometary debris is still a matter of some dispute. But we really do need a much more thorough explanation of that centaur population and a much better understanding of the environmental consequences of running into a dense stream of cosmic dust and comet fragments. So while it would appear that we've got the conventional threat from asteroids and comets, maybe not under control, but we're at least moving that way, we have this whole new threat now from the disintegration of centaurs. At the moment, that's not really anybody's priority. In fact, it's really only in the UK that scientists have been looking at this. A number of papers have been published, but being the UK, of course, no action taken. And on that, I'd better move to what we do up here. Now, at the SpaceGuard Centre, we have a number of instruments. When we first moved up here, the prime instrument was a 13-inch apochromatic triplet refractor, which is absolutely ideal for looking at planetary objects, small objects like distant galaxies and so on, but not really what we want for the work we do at the moment. We're into that tracking game. We're not into a search program. We don't have the right sort of telescope for that yet. We track asteroids that are picked up by the survey programs mainly in the United States. So for that, we need something else. We have a 14-inch Schmidt Cassegrain with a perfect field of view for exactly what we need. For example, that's a picture of the moon. The field of view of our 13-inch refractor, the big fella, is only that big. Not really much good for what we're doing because of the uncertainties that we're dealing with. So our tracking telescope has a much wider field of view, and that's frankly about as good as it gets for what we're after. What it's no good for is a search program. If you're looking for stuff, you need a whopping great big field of view to see a big wad of sky. So if we want a search program, we're going to have to get a telescope with a big wide field of view, rather like that one. That's a 24-inch Schmidt camera. Not technically a telescope, there's nowhere to look through it. It's purely photographic. But with a single photograph through that, you can fit 10 full moons across the frame. So as a search instrument, this is absolutely perfect. It's probably also worth mentioning that telescopes with that sort of field of view are rather like hen's teeth these days. Prior Second World War, what most astronomers spent their time doing was mapping the sky in ever-increasing accuracy. For that, you needed telescopes like this. Nowadays, of course, people want very high-resolution images of very small patches of sky. So wide-field telescopes like the Schmidt have really almost disappeared. This one, however, was in Cambridge at the Institute of Astronomy. But for the last 35 or 40 years, they've really not been able to use it properly because of light pollution. Cambridge has spread. So at the back end of 2008, this instrument was offered to us to redeploy, if you like, to the centre up here as a search instrument. Bit tricky, a big beast. That's what we've got above the floor in the dome. There's significantly more below the floor. In fact, it stands about 15 feet high and it weighs about 7.5 tons. And it all has to come out through that slit in the dome. Well, having been offered it, we set up the project. It's called DRAX, not because DRAX stands for anything. We don't do acronyms. Projects here are just named after James Bond villains. But the idea of this was to get enough resources to relocate the camera, build a dome for it, and then bring it back into service. We removed the camera from its dome in Cambridge. The optical tube was fairly simple. The base assembly and the fork was not. However, with a good crane driver and a little bit of jiggery pokery, it came out of the dome quite nicely. And it was then a case of loading the whole thing onto a flatbed and driving it to Wales. Here, of course, we had nowhere to put it. So one of my volunteers actually owns an engineering company down in the valley, and he was able to give us some space in his factory to give the thing a quick once over and then prepare it for long-term care and pres. In fact, we shrink wrapped it, nitrogen filled. It could stay like that for 25 or 30 years if necessary. But then we had to work out where to put it. Well, the only bit of ground that we could find that was reasonably suitable was our picnic area. So that had to go. One of my other volunteers is actually an architect, and he came up with the drawings and the plans for the new dome. What we couldn't do is afford to employ builders or anything. So we decided to do it ourselves. We learned significant number of skills that we never really wanted in the first place, but off we went. We actually lifted the base assembly of the camera onto its concrete plinth in the building at a fairly early stage. We needed that to build the upstairs floor. Then came the problem of the dome. Now you can buy a 26-foot dome if you've got £178,000, which obviously we didn't have. Like, our budget for this was a big fat zero. So we decided to do it ourselves. We learned how to make fiberglass sections. We actually put together 27 of them. 26 for the dome, one spare, because you're bound to break at least one. But each of them, after manufacture, had to be trimmed, sanded, primed, and then top coated. Once that was all finished, we could put it together. Now, the day we decided to put it together had a sparklingly good weather forecast, so not a big surprise that about 2/3 of the way through the process, it began to pour with rain. Not a problem for us, but a huge problem for the sealant that goes between the sections. So we had to stop. What we didn't know was that on the following night, there was a very short but very sharp storm, which effectively crashed the whole thing. But it's fiberglass, and you can fix fiberglass. So the following weekend, everybody came back up again, and with the help of bits of farm machinery and so on, we managed to get the whole thing back together again, and we ended up with a perfectly good dome. Loads of cracks and tears and so on, but they could all easily be fixed from the inside. As soon as that was done, though, we could then lift the tube assembly onto its mounting in the building, and about 15 minutes after that, we could lift the dome. Now, where we stand at the moment with this project, it's, well, for the last 15 or 16 months, of course, everything's been completely shut down. The volunteers couldn't come up, no income, of course, so everything's sort of plateaued out, but we're just now beginning to get back into the swing of it. For example, we're working on both the camera itself and the dome and building. These are the new electrics. My electrical engineer put this lot together during lockdown. We've installed them, tried them. Everything works absolutely fine. On the mechanical side, both the right ascension and declination drives and gearboxes have been completely stripped, refurbished, cleaned. And in fact, we now have two completely workable drive systems, up and down, round and round. The big problem for me at the moment is the shutter, the sliding bit of the dome that allows us to see out. Now, originally, it was going to be a nice, simple, elegant system. That's what it should have looked like. But you give two bored engineers 15 months of nothing to do, and trust me, they're going to come up with a nightmare. And sure enough, we have a nightmare. I say it's a nightmare because I don't really know how it works. They're both over the moon. Last Saturday, they proved to me that this system works. It actually lifts the shutter before sliding it. So I'm a happy camper, but my God, is it complicated. That aside, we have one other thing to really get to grips with, and that's the imaging system inside the camera. Originally, it was a glass photographic plate, 6 inches across. Now, obviously, that's not going to happen now. So we're replacing it with a rather nice research grade CCD camera. In fact, we've already had the custom mounting built for it. We're just not quite ready to install it yet. But what we won't get out of that is that full 5-degree field of view. If you wanted a CCD chip that big, you'd be looking at 7 figures. But we'll certainly get at least 2 degrees by 1.5. And frankly, that makes this system very, very viable. It's going to be a very useful search system. Just as an aside, over lockdown, we've used the Dome on a couple of occasions as a TV studio, which is slightly alarming. We've also had up here a number of fairly high-priced visitors. This is just a random selection. If you don't know who the guy bottom left is, that's Rusty Schweikert. He was the command module pilot on Apollo 8. He also runs now the B612 Foundation that deals with near-Earth objects in the United States. So we do have quite a lot of high-priced help. What we don't have is any external funding. The British government does not consider near-Earth objects to be a problem of any description. It doesn't even appear on the Cabinet Office National Register of Risk. If you're not on that list, you get no funding. It's as simple as that. So sadly, the UK is completely out of this game. So we do it ourselves. It's really as simple as that. But to go back to about halfway through, we have a problem. We know it. We have a problem that's very, very rare. But when it does happen, there is no upper limit on the amount of damage that a near-Earth object can inflict on this planet. Mass extinction's a minor thing. But this one is avoidable. It's not a case of we can't do it. It's a case of we can't be bothered to do it. So I leave you with a very simple question. Are we any smarter than the dinosaurs? They're extinct because they didn't have a space program. Well, we do. And the question is, are we just going to sit here and let it happen? And on that note, I think I better stop. So, Simon, over to you.
Well, thank you, Jay. That was absolutely fascinating. What an interesting talk, and what a unique project you're involved with there. And I guess it's thanks to you and your volunteers that we've been made aware of these things. I hope you got time just for a couple of questions, if that's okay with you.
Absolutely, but can you give me 2 minutes?
Yeah,
good.
No.
Well, you haven't got any choice, actually, but I will be back in a couple of minutes.
Go for it. Yeah, that was very interesting, wasn't it?
Yes, bit frightening.
It is. It almost seems to be one of these problems that everybody's going to ignore, like that picture that he showed with the heads buried in the sand, until suddenly they go, "Oh right, okay, yeah, that could actually happen."
Well, we did with the pandemic threat of that.
Yes.
It's been threatened for decades, I'm sure.
I was going to say, so that's exactly what happened, wasn't it, with what we've just gone through, and they funded some research into that.
How we It's how we do it. We're being warned about problems. Yeah.
So
Water thing, like Jenny spoke about, didn't she? Water wars.
Yeah.
I'm sure there will be a problem with
I
water.
hope. Sorry about that, but when nature calls, there's nothing you can do about it. Right, I'm going to stop sharing my screen now.
Okay.
At least I would if I knew how to do it. Oh yeah, here we go. Yeah, stop share. There we go. Yo, back to square one.
Yeah.
Jolly good.
Okay.
Right.
Jay, I had a question sent in here saying, hold on, let me be well, I've got my iPad here. What do you think needs to be done to get the government to fund the project? There's an easy one for you to start with.
An impactor on Parliament, I would suggest.
Well, a small group of assassins wouldn't go bad, but it's very difficult to say. I mean, to be perfectly frank with you, we've been in this game now for best part of a quarter of a century, and there is absolutely nothing that we found that makes any difference at all. Well, just as an example, when we briefed the Secretary of State some years ago, the first question was, is this going to happen before the next election?
Yeah.
Yes.
And when we said, well, you know, hopefully not, you can see the shutters come down.
Yeah.
Also, there's a view that the United States has got the whole thing under control, so we don't have to worry about it. Well, wrong answer. You ask the people in the United States and they'll tell you the first thing they need is lots and lots of international cooperation. I said that the European Space Agency is involved. It is, and we are part of the European Space Agency. But within ESA, the member nations can opt in or opt out of the various projects, and the UK opted out of the Near Earth Object Project. So we're not involved with that either. So where do you go? Repeated requests for comment, information and so on from government simply produce drivel. I just asked them recently, who is your spokesman who's responsible for this? Answer was the none. They said, well, go and talk to the UK Space Agency. They deal with it. I spoke to them and they went, no, we don't. Nobody's told us to do that. And so you start going round and round the loop. In the end, you say, sod it, we'll do it ourselves.
Yeah. And we've just been talking, just when you nipped up there for a second, we were just saying, though, Sue said that it's very reminiscent really of the pandemic, in that, you know, we knew it was there, but it would never really happen. And then suddenly it's happened and we're all shocked. But the difference seems to be that with the pandemic, they were funding scenarios and emergency planning for that, whereas this just isn't being funded at all.
No, it isn't. Well, not being in the UK. I have to say the United States for the last 25 years have been pumping quite a lot of money into this. Not a massive amount. I mean, NASA's initial budget for this was $1.4 million a year. That's slightly less than the US Marine Corps ballpoint pen budget. But that's now been upped quite a lot. UK,
yeah.
I mean, we did have a government task force look at the whole thing back in 2020. No, not 2000. We actually went to brief the then science minister, David Sainsbury, and he agreed to set up the task force. They spent a whole year tromping around the world, talking to all the shakers and movers in the game. And they came back and produced a really, really good report. So good that I know that NASA still use it as their sort of intro to near-Earth objects, if you like. They made 14 recommendations. One of those recommendations was implemented. They set up the National Near-Earth Object Information Centre at this big space centre in Leicester. Well, as soon as the government stopped paying to run the website, they canned that at Leicester, and there was nobody. So we got in touch with the brand new then UK Space Agency and said, look, you know, who's doing this? And they went, oh, nobody. So we said, fine, we'll do it. Oh, well, you're not going to get any money. No, we'll just do it. As a matter of fact, we've been doing it for the last 10 years, so it doesn't really matter. We can just add another name to the SpaceGuard Centre. But you know, you could get all wound up about it and get bitter and twisted, but frankly, life's too short. We've got far too much to do here to get excited about that sort of thing.
Yeah. And what's the Yanks' view on this? What's the Americans' view on, you know, us not funding anything, and you kind of sat there as a group of volunteers doing it while they do? It's the wrong phrase, but while they do the paid graft, you know, you guys are sat there doing the voluntary graft. What's the US's view on it? Is it just a case of, oh well, there go the UK again doing it on the cheap?
Yeah, in a word, no. I mean, we work quite closely with the individuals in the US who do this. In fact, Linny Johnson, who runs the Centre for Near-Earth Object Studies for NASA, he and I were majors together years ago. General Pete Warden, who was then the Deputy Director Operations for the US Air Force Space Command, wanted to set up a Near-Earth Object Studies office as part of the US Air Force. And he wanted me to go and work for them. Now, I was a major in the UK, and he wrote to the Ministry of Defence and said, I want this bloke for at least 2 years on secondment. We will pay all the expenses and his salary. To which there was zero response. The MOD never even answered his letter. So they actually ended up with a Frenchman, which is a bit sad, because one of the things Pete Warden told me is, you know, it'll be over my dead body that we get a Russian or a frog. And they ended up with a Frenchman, purely because the MOD, you know, ignored it. So I'm very clear in my own mind that the United States would kill to have British support on this. Apart from anything else, both NASA and the US Air Force have been mandated by Congress to make this an international project. And on that basis, they get their funding. Well, it isn't international.
Yeah. It's interesting that, sorry, everyone, I've hogged the questions here, just having a chat. It's quite interesting that space weather is funded by UK government, you know, and there's a space weather centre at the Met Office. They've managed to get it, obviously, because of the direct impact on satellites that things like solar storms can have. So it seems that there's an arm to be twisted there, but it seems that when there's a planetary impact potential from this, it's kind of, well, no, we're not going to give you any money for it. Well, it seems to me what you're doing is, you know, space weather we can predict pretty easily with a SOHO satellite now. It's pretty straightforward. But what you're doing is far more complex.
There are three aspects that the European Space Agency Space Situational Awareness Project address. You've got space weather, space debris, man-made space debris, and near-Earth objects. Now, as a member nation of the European Space Agency, the UK has signed up to the space weather part of the project and the space debris part of the project. They did not sign up to the near-Earth object side, which means, of course, we can't get funding from the European Space Agency. Detlef Koshny, who runs the Near Earth Object segment, is desperate to get some funding to us, but he can't because the UK didn't sign up for it. It just seems to be a mental block.
Yeah.
That this is not our problem, or it's not going to happen, or, you know, we're British and nobody does that sort of thing to a Brit. Well, you know, stand by for mass extinction, boys.
Yeah.
I mean, it's not going to happen in your lifetime or mine, but it will. And if we're not ready for it, it's going to come as a great big effing surprise, you know, which is probably not the way to go about it. And the amount of money it would cost was described by Sir Crispin de Kell as, from government point of view, a rounding up figure. You know, we're not after millions or billions. It's frankly dirt cheap, and it's like an insurance policy. You don't insure your house against fire in the expectation that your house is going to burn down. But if it does, it's awfully nice to have it.
Yeah,
you know,
you do get the feeling it's going to take an event where it kills a few people for, you know, for politicians to sit up and think, oh well, perhaps we should chuck a few quid.
Well, this is what we thought when
Chelyabinsk.
Yeah, this is what we thought when the Chelyabinsk event happened. Yay, hey, here we go. There's the wake up call. It's all going to happen, and absolutely nothing happened. Pete Warden, I think, had the right idea when he said what we really need is something that kills more people than 9/11 did. Then we'll have people's attention. I mean, the problem is that it's so rare. Good news, you know, it's good news. It's rare. Don't get me wrong, but because it's rare, nobody's seen it on the news. And if you haven't seen it on the news, it doesn't happen.
Yeah, absolutely. Absolutely. Yeah. I
think it would have to hit London, Jay.
Say again?
I think it would have to hit London, a relatively small impactor.
Well, yeah. Couldn't happen to a nicer place. Come on. Unless, of course, it was Birmingham.
You need the funding from the London politicians. You love the place.
Well, trouble is, if you took out Birmingham, I mean, the politicians wouldn't notice, would they?
Absolutely. Has anybody got any other questions for Jay? I've got one here for you, Jay. Somebody sent in to me, which is what got you interested in SpaceGuard in the first place? And I guess that goes back to, do you have a deeper interest in astronomy? Is that something that goes back a long way, perhaps to your military background?
No, my military background was shooting down aeroplanes. This is actually pretty much the same thing. I mean, technically, it's not that different. You know, you got to find them, you got to fix them, and you got to destroy them. But no, my interest in this was peaked when those comet fragments, Shoemaker-Levy 9, hit Jupiter. You could actually see the scars on the planet with a fairly small telescope. Now, as a result of that, I wrote a paper suggesting that if it could happen to Jupiter, it could happen here as well. And what did we have in place in the UK to deal with such an event? And frankly, the more I looked, the less I found, until it became crystal clear that there was absolutely zero. And it was at that point then SpaceGuard UK started up. We actually ended up being the largest SpaceGuard organization in the world at the time. Everybody who was a key player in the game at that time was a member, and we did have, you know, fairly significant clout, which we still have, but not in the political theatre, because politicians can't understand probability. It's as simple as that, you know. And time. Yeah. Let's face it, a politician doesn't give a rat's if it's going to happen when he's no longer in power.
Yes. Well, that's
It's not my problem, you know. And we're looking at something that may not happen for thousands, even tens of thousands of years. It may happen tomorrow. I don't know. Well, I do, but it's not going to happen tomorrow. But, you know.
If we leave our phone numbers, Jay, can you give us some advance warning?
Yeah, but I mean, it's a mindset that is just almost impossible to change.
Yeah.
And
It
on
needs
that
to be made
basis,
trendy.
well, all I can say to the politicians is we'll do it ourselves.
Yeah.
And we are. We're going to end up, if and when DRAX is up and running, with a very capable search and tracking system, which has been put together by a bunch of volunteers in Knighton, for Christ's sake. You know, at a cost of slightly less than it would cost you to buy a Porsche Carrera.
And
I
again,
used to spend the budget we've got for the entire project in a morning on the missile range in the Hebrides. I could shoot that much money downrange into the sea before lunch. Hey,
amazing. You know what? It may well turn out that it's a better outcome because it's been built in the way that it has, with the passion that it has, and by amateurs in the true old-fashioned sense of the word, who probably know a lot more about it than perhaps some professionals. It would just be nice to get some money coming your way to help fund it.
Well, without being mercenary about it, if you go to our webpage, the SpaceGuard Centre webpage, you will find a page called DRAX, and under that you'll find a page called Donate to DRAX.
yes.
I thought I'd just slip that one in quietly. Without being stupid, of course, for the last year and a half, the project income has been that much. Because we've had no visitors up here, we've had no people around. So we're pretty thin at the moment.
Well, what we'll do, Jay, is we'll put a link to the direct link to the donation page on the YouTube page and on the Facebook page as well, with the link to that.
Well, that would be jolly kind, you know. I mean, we're taking visitors again now.
And what about we?
Sorry. Somebody's.
And I was going to say that was my next question actually. When we were talking before the meeting started, we were just saying about visitors, and of course you have visitors there. Of course, essential that they pre-book and that they turn up.
Oh yes, yeah. If you don't turn up, then I get very, very sad because we can only take one household at a time at the moment, which means if two people, you know, a married couple book for that tour, that is their tour. We can't take anybody else. So if a family of 6 phones up, we can't take them. If those 2 don't show up, I'll track them down and kill them. I mean, it's pretty straightforward.
Stick a bat up the nightdress.
Well, to be honest, I'm actually getting quite heated about this because it's so.
I saw it on the Facebook page.
Yeah, it's just so rude, you know.
Absolutely.
But hopefully, well, because we're in Wales, of course, all the rules are different. I mean, even we can't quite understand what we're allowed to do and what we're not. But it does look like next month, restrictions will be lifted to allow us to take in a few more. But I don't think it's going to be, well, it's going to be a long time before we're back to where we were, which is fair enough. Don't complain about that at all. But we should be able to take a few more.
Well, when we're back to where we were, Jay, it'd be great to organise a society visit, perhaps up to you, when restrictions are fully lifted and we've got unlimited numbers. Perhaps it'd be great to come along and visit. We did speak about it a few years ago, but I think when COVID is over, and hopefully it will be, perhaps it might be nice to organise an evening for us to come up and visit you properly
Well, absolutely no problem there at all. It'd be delightful. It really would.
Fantastic. Excellent. Has anybody else got any other questions before
I have. I'd like to add, Jay, you live in a relatively dark part of the country. Has the local government been cooperative in imposing any lighting ordinances to keep your dark sky?
Not officially, because we haven't asked them.
Mm-hmm.
But unofficially, we're copied with all the planning applications for the local area, and we can object then on the basis of lighting. I mean, we're not trying to be obstructive, but I mean, as an example, there was a planning application about a year ago for a massive chicken sort of shed with huge spotlights and things like that. We just simply pottered down the hill, spoke to the bloke who put in the application and said, listen, matey, if you put it in as it is, we will shoot you out the water. You know, why not think about lighting that points down, not up, and all the rest of it? And he went, yeah, good plan. So that all went away. They're actually not going to get the permission anyway, but our local town, Knighton, that's so far down the hill. I mean, they can flash whatever they want, and it's not going to make any difference up here. Prestine, which is to our south in exactly the direction that we look, because that's where the ecliptic is. They've got a very strong dark skies campaign running at the moment, and it's highly likely that they will be the first dark skies community in the UK fairly soon. We don't have a problem in that we tend to sort of shoot them down before they get to the planning stage, if you see what I mean.
Yeah. Another thing I'd like to ask you, Jay, is when I visited your site, which was over a year ago now, you had a stone circle. Is it an original megalithic one, or is it one you've contrived yourself to do some solar observation?
Firstly, it's not old. No. And secondly, no way did I contrive it.
Oh, see.
It was built by the original builders of the observatory, who are 50% genius, 50% why the hell did you do that? And the stone circle comes into the latter. But it is a completely functional astronomical instrument. The stones are all aligned precisely at what they say they're aligned with. So if you really, really want to go and stand in the middle of it, then you can do all sorts of fun stuff.
Yeah, I can remember when it was advertised for sale, the bungalow with the observatory attached. Yeah.
I've been here 20 years and I've never stood in the middle of the night. I can assure you of that. But no, it's fun. It scares the crap out of the locals. They think we're deeply into flying saucers and things like that. We might.
So was
possibly...
it, Jay, was
yeah, go on.
I was just going to say, was the bungalow and the observatory then built before you got there? Was it a project? You know, was it somebody's dream to have that set up?
Oh hell yes! I mean, if we built this place, it wouldn't be anything like it is. I can assure you of that. No, it was built by a couple who thought it would be a really, really good idea. Wow. And they basically did the whole thing themselves. I mean, it's awesome.
Yeah.
But they were only here for about 5 years, and then Brian came up with some sort of health issues, and they had to sell it on and move to Spain, of all places. The guy who actually owns this place actually got in touch with me when SpaceGuard UK first started and said, I rather like what you're doing. Can I help? Would you like my observatory?
Wow.
Yeah, you build us a house and we'll move in. So he did, and we did. We only see him about once a year. Well, we haven't seen him for a couple of years now, but he just leaves us alone and lets us get on with it.
What a great story. There's a
Oh,
film
it's
in
all
that.
good. It's all good fun, you know. Well, luckily that offer came at exactly the same moment as I decided it was time to pull the plug on the forces. They said, you know, from here on in, you're going to be behind a desk. Well, I mean, that's just death, isn't it?
No.
So I decided to go. Andrew said, "You want my observatory?" We said yes. Boom. The day after I took off my uniform, we hopped in the car and drove up here.
Fantastic. What a brilliant story.
Well, it worked, you know. We've been here, well, 20 years and a fortnight.
Love it.
But yeah, it's all good fun, you know. And my gallant group of volunteers show up every week, and off we go.
Fantastic. Brilliant. Well, listen, Jay, thank you so much. Has anybody got any other questions before I let Jay go?
Has it spurred the interest in astronomy in Knighton, and have they started an amateur astronomy group?
Well, we have the Marches Astronomy Group. Obviously,
course,
that's been pretty moribund since lockdown. But you know, come the day, we'll be restarting. We'll relaunch. We'll get going again. And
there's a Clun Society, isn't there? Isn't there a Clun Society?
A what?
Clun Society. Is there one at Clun?
I'm not sure there's one at Clun. There's another one just
Chapel
down
Lawn.
the hill.
I've visited one at Chapel Lawn.
Well, yeah. That's ODAS, the Office Dyke Astronomical Society. I've spent 20 years trying to link with them, you know, in the nicest possible way.
Yeah.
But they seem to have this fixation that anything that happens up here is not good.
Circle.
I think it's mainly because the original people up here upset them massively somehow. I don't know how, but there's great big gloom about that, and that's sort of carried over to us. I'm not going to die in a ditch. I mean, our people are really good, and we've got a lot more people than they have. But you know, I'm not going to get into a bitch fight about that one.
Excellent. Well, listen, Jay, thank you so much for your time tonight. It's been an absolutely fascinating evening. I think we've learned an awful lot and stuff that probably we kind of knew that was milling around in there somewhere, that perhaps we should be interested in it, but you've certainly brought it to the fore as a perhaps we should be slightly more interested in it than we have been for the last, in my case, 49 years. So certainly, I think the work that you're doing there is wonderful. Thank you for that. Please do keep it up. And we really will look forward to seeing you and coming on a visit, perhaps to see you when we can.
Well, as soon as we can, you give us a call and we'll sort something out.
Fantastic.
Jay, I know that you folks get a skeptic, but I hope you find a craft full of aliens before you find an impactor.
Don't you worry about that. No, all too much like fun. Come on. Look, I'm going to bugger off.
Thank you, Jay.
Thank you, Jay.
But thanks ever so much for inviting me.
Thank you. And we will see you soon. Cheers, Jay.
Enormously good fun. I'll see you anon. Okay, bye-bye. Then. Bye for now. Bye.
Alan, could you stop the presentation? But you should be able to. It says end meeting.
Yes, end. Yeah.
No.
Thank
you all.